Okay, so we've got dude on scale in an elevator, as you do. Okay, so dude on scale. So dude, and we'll just pretend the whole floor is the scale, which is fine. So dude is on scale. And if I'm drawing a free body diagram of dude, so there's technically that he's standing on the scale. He has weight of, or not weight of, he has mass of 65, so, or 75. So it's 75 times 9.81, 73575, okay. Weight equals 75 times 9.81, and I already forgot the number, 73575, 73575. And then there's a normal force with the ground. Okay. So calculate the scale reading. I'm assuming that means what's the normal force if the elevator accelerates upward at a rate of 1.2 meters per second. So if we're accelerating upward at 1.2 meters per second squared, then our free body diagram, sum of the forces, well, there's nothing in the x, sum of the forces in the y is, n is going up, and 735.75 is going down, and that equals mass times acceleration in the y direction. The mass is 75. Change my colors here. The mass is 75, and the acceleration, because it's upward, did it say upward? Upward, 1.2 meters per second squared. So if you want to do this, you can do meters per second squared, and kilograms times meters per second squared is newtons. So our units check out, because this is also newtons. But the reason I don't do it is because n looks like it's newtons, and then I get confused, so I just start dropping units. So I've got 75 times 1.2, and then I'll have to add that thingy. Oh, and then that's it. So normal equals 82575. 825.75 newtons. See, that's why I don't like it. Newtons. Or if that really bothers you, it bothers me sometimes. So normal force of the scale or something like that. 800 and something newtons. So even though his weight is only 730 newtons, the floor is feeling his weight at 825 newtons. Okay, and then the second question was, what if it moves upward at a constant speed? Well, heck, I can do that, because if he's moving at a constant speed, then it's mass times acceleration in the y direction, but acceleration in the y direction is 0. So the normal force is just straight up 735.75 newtons. Look at me. I'm kind of a genius. Okay, that's all there is there. Man, they really talked about this problem for a while. Okay, 2 attached blocks. We'll go ahead and do this one too. Frictionless horizontal surface pulled by a light string, so massless string, frictionless massless pulley, so we've assumed the cow is spherical. Find the acceleration of the blocks of the tension in terms of M1, M2, and G. Oh, okay. So acceleration, and it's telling me which direction it's going, which is helpful, because if it didn't, well, I guess since it's frictionless, that's how it has to go. Okay, so I've got, and I'm never going to look at their pictures because I never like the way they do it, because, you know, you get your own way of doing things, and then everybody else's way of doing things is stupid. So mass 1, mass 2. Okay, and they're attached by stuff. Oops. They're attached by, stuff, like that. Okay, so mass 1 is sitting on the ground. So there's a normal force that keeps it from going into the ground, normal for 1. And it has a weight, and there's a tension in the string. Okay, so that's 1. So the weight of number 1. Then I know that it is accelerating that direction at something called, did they just tell me A? A1. Why are A1 and A2 different? That doesn't, okay. I can't see how they would be different. Wouldn't they have to be accelerating at the same rate unless the string is changing length? Please tell me at some point we say that the same coordinate system. Oh, I see what they're doing. Okay. So I'm going to do it my way, and we're going to get to the same answer. So it's accelerating that way. Got it? Okay. Now, block 2 is not touching the wall. So there's no normal force against the wall. There is a tension pulling up, and there is a weight pulling down. Now notice that this is the same tension, so I labeled it with the same letter. This was a very casual thing for me to do, but it was super duper, duper duper important. Same T, because it's the same rope. Okay, so if I've assumed that block 1 is going to the right, without getting too much into it, because there's actually a whole lot of math that you can do, especially when you have like more than one pulley. If I assume in this picture that block 1 is going to the right, I can assume that block 2 is going down, and they're going the same speed, same acceleration. So I'm going to draw my acceleration here, like that. Okay, so for the purposes of this discussion, like if it turned out here that A was 5, you know, I hat, then here acceleration would be negative 5j hat. Okay, so they have the same magnitude, they just have different directions. Does that make sense? So their magnitude is still 5, it's just what direction is it pointing? Okay, so it's not actually 5, I'm just calling it 5 for no reason. I'm just going to call it A. Okay, so now I've got my sum of the forces and things. You can go over here for a minute. Whoa, I don't know what just happened. Okay, so I've got the sum of the forces in the x direction for this guy is I have weight 1 pulling down. Now weight 1 is just mass 1 times gravity. So mass 1 times gravity plus the normal force is equal to mass 1 times the acceleration in the, we'll just say the x direction. Nope, I did that all in y, so I'm just going to change this to y. Y direction. Okay, y direction. Now it's not moving uppy downy. I don't even think it asks for this, but I now know that the normal force is m1g. I don't think it's going to come up. But let me go ahead now and do some of the forces in the x direction like I meant to, and it's just the tension. And this is now equal to mass 1 times acceleration, and it's pointing in the correct direction. Okay. So, T equals m1a. Done. Now let's look at this dude. All right, now if I look at the sum of the forces in the y, I have T going up, W2 going down. Now weight 2 is equal to m2g. Okay, m2g equals mass times acceleration in the y. Okay, so T equals T minus m2g equals mass 2, and acceleration in the y, what did we decide? We kind of gave the example of like here, it would be 5I hat, and here it would be negative 5J hat. So in this case, A is 5, here, I'm calling it A is 5, here A is negative 5. So I'm going to put that in as like negative A. Because if I'm trying to write it in the same terms of A as the other guy, this is a downy A, not an uppy A. So this A is going down. Does that make sense? I hope so. That's like the biggest leap of faith right now without, there's actually like math I can do to prove this, but I think it's going to make it infinitely worse. And I think 90% of you are going to be like, no, it's cool. And the other 10% will be like, it's not cool, but fine. And if you really don't like it, let me know and I can try to fix it. Okay. So basically it's the same magnitude. It's just going down. Okay. Then I can take this dude. Oops. Then I can take this dude and plug it in here. So M1A minus M2G equals minus AM2. Wait, what was I even supposed to get? I don't even remember anymore. That's the problem with these things. Oh, find the acceleration of the blocks and the tension. Well, I already got the tension. Well, hold on. Acceleration times M1 plus M2A equals, yeah. So the problem with solving these now is it's like, look, I solved something, but you can't really tell what I did because it's all algebra. And I mean, I love algebra as much as the next squirrel, but this is just garbage answers. But don't memorize this. I'm just now doing math for no reason. Look, I got an answer. Nobody cares. Really, the crux of this problem is getting this. That's the most important part of this problem. The rest of it's algebra. Who cares? It'll potentially be different depending on what all is going on. But what's really important here is, in this case, acceleration is going down. So it's the magnitude of that acceleration in the negative direction. And if I get that negative sign wrong, then everything else is wrong. Okay, but that would make sense because think about it. And if you're still kind of iffy on it, think about all these values in this number here would be positive, right? So again, mass is positive, gravity is positive. You're like, no, it's negative. No, it's not. G is 9.801. It's just, or 9.81. It's just, we put a negative sign in front of it sometimes. Mass is positive, so that's a positive number. So whenever I come over here and I put it in here, I've got my negative number like that. So that's how I get my negative thing like that. So that's really where we're trying to go. It's far less important that you're getting the answer than you're understanding kind of what we're doing and how we're getting these equations.